Welcome, everyone. It is my pleasure to moderate today's tinyML talks. My name is Kautar El-Maghrawi, and I'm a principal research scientist at IBM Research. And it's my pleasure today to present our speaker today and our talk as part of the ongoing tinyML talk series. Today we have a very special session that addresses neuromorphic analog signal processing by Alexander Timofeev, the founder and CEO of Polyn.ai. So before we get started, I would like to express our deep thanks to all our strategic partners for committing to take tinyML to the next level. And special thanks to the tinyML Talk webcasts, analog devices, ion devices, ARM, Deep Light, Edge Impulse, EMSA, PhotoHub, Green Waves, Gravity Inc., Hot-C, Image IOMB, ITMITS, Calic Tech, Latent AI, Nota AI, OctoML, Profees, Kixo, Qualcomm, Reality AI, Rexen, Renesas, SAP, Seed, SensiML, Silicon Labs, Sony Semiconductor Solutions Corporation, ST Microelectronics, Stream, Analyze, Synaptics, SynSense, Sentient, NTDK, InventSense. Thank you all for partnering with tinyML and driving the next wave, in this revolution. I would like also to remind our audience today that we're preparing for the next tinyML EME at the EMEA Region Innovation Forum, and the goal here is to connect, unify, and grow the tinyML EMEA community. So this event will take place on October 10 to 12 this year. And this is the link for the event. I hope you visit, check this out, and register. The event will be held in person in Cyprus, and the call for participation is open until the beginning of August. So looking forward for your contributions and participation. And also, if you're interested in sponsoring this event, the sponsorship is available by contacting this email address. Our next tinyML Trailblazer series, we also have, a great speaker, in store here. And this is, again, the success stories with Joram Zilberberg, who is the CEO at EMSA Visual Sense. So this will be live in July 6th at 8 a.m. PDT. And you can register, the details for registration is mentioned here. I hope you can join us. And of course, this is just reminding everyone that the tinyML communities continue to grow up. So currently we're at 10K members across 45 groups and across 36 countries. This is really huge. And on LinkedIn, we're 2.9K members and more than 7K followers. So we're very thankful for the engagement for all the communities. And together we really can do great things. So hopefully this will keep growing. And if you're interested, if you're not part of this, please join us. So the links are here. And of course, you can join and subscribe, the tinyML YouTube channels to get, all the updates and notifications about, all the great talks and discussions and forums that are happening as part of the tinyML series. So currently we're at 7.1K subscribers with lots of videos. Everything is available online, including this talk will also be available very soon. So this is a great resource that benefits the entire community. Our next tinyML talk will happen on Wednesday of June 29th. And the presenter will be Thomas Basicolo, Marco Zinaro, and Alessandro Grandi. And the talk here is about the Smart Weather Station, the tinyML challenge. So this is also another great, interesting talk. I hope also you can join. And so it's really my pleasure to introduce today's speaker, Alexander Timofeev, who is a serial entrepreneur in high-tech startups and a venture builder with more than 20 years in the industry and the vast technical and business experience in industries such as nanotechnology, autonomous system, and super hard materials. Prior to founding Polyn, he founded Eyeglass Technology, Inc., a company that developed novel electrochromic smart glass technology. He also built the core team and product concept and successfully sold the company at the end of 2020 to a strategic investor. He's also the founder in 2010 and managing partner at FBI Innovation Fund VC and an early stage venture investment management company. The fund focuses on earlier stage innovative companies, developing clear product, concepts, and strategies, and working with venture firms or partners for subsequent funding rounds. As a managing partner, Alexander is responsible for greenfield and development from early stage to growing business. It's really our pleasure to have you, Alexander. Thank you so much for your presentation today.
Yes, thank you. I'm happy to introduce our project to tinyML audience. The company name is Polyn.ai, and we focus on a new product in analog neuromorphic segment. But first, I need to identify where we're working and what we're doing, because in neuromorphic landscape, it's a lot of project and a lot of buzz about big data, big neuromorphic network, which is focused for machine learning and brain activity simulation. So we focus in other direction. Our project and product focused on sensor data pre-processing. That is like nature work, like our eyes, ears, doing efficiently pre-process raw data for our brain. And that is very important in our time, because the concept of digital signal processing was launched more than 40 years ago. It was a very successful, very important hardware innovation, which opened a lot of new products and markets sometimes. But now we think it's a time to introduce neuromorphic analog signal processing, using analog signal processing instead of digital. Why it's important? Because the sensor volume and the volume of the data we generated sensors, it's growing like a tsunami. And digital core in any level, it's overloaded with raw data, especially if we're talking about mobile devices and solution where always on data processing with low power, it's important. And we think it's time to define new level of hardware, tinyAI, and that is our definition, tinyAI solution, which be like stated between sensors and digital core, and take this raw data, like dirty work from digital core, close to the sensor, and extract useful information from raw data. And now that solution, especially if you need ultra low power, low latency, always on application, it's not easy to achieve this in digital schematic, in digital hardware, because technology is very well scaling up for big data, for ultra high performance processing. But if you go down and use neural net for data processing, it's very difficult to scaling down below 1 milliwatt level of power consumption, especially again, if it's always on solution. And analog neuromorphic data processing, it's much more power efficient for that solution. Our brain, it's a great example of power efficiency, just 20 watt power with high computing volume, but it's still not available practical technology, practically available product on the market using analog neuromorphic data processing flow. It's a lot of discussion the past 15 years about that. Few attempts to present, still many interesting research, but all of that focused on new hardware solution development. We go from other direction. We use the existing hardware, the well-known mature technology process to present analog neuromorphic core. I will show the short video about the concept, how we built our NASP product. So what is the core of technology? First of all, we decide to split neural net training, development, and inference. If you work on close to sensors and you need to process raw data, in 99% of situation, you don't need update your model. So that we trained model in current digital environment as is. We use the standard Flow, Terrace, PyTorch, TensorFlow, what every mathematician use it. And when we train neural net and we can see what part of neural net is fixed, because when you typically, again, that is a very common situation in data pre-processing, that after a few hundreds or thousands of training cycles, the biggest part of your neural net is freezed. So you can identify fixed part and split between fixed and flexible part of neural net. Then we take this fixed part and using our compiler, generate the physical representation of this mathematical model. And this representation consists analog neurons. So we don't have digital part based on operational amplifier, connection, and weights. Weights are representing as fixed resistors array. So we have like a mask programmable core. And then we generate physical layout, which is in standard GDS2 format, which we can tape out in standard fab process. So that is how works this concept. To use this transfer learning concept and convert fixed part of neural net to analog neural core and still have a flexible part if it's necessary. Not for all application, I will show this later. Not for all application you need a flexible part, but for some of them, yes, you need a flexible classifier. That's still in digital, but the data flow through digital part, it's reducing dramatically, more than 1,000 times. So the final effect, we have 100 times less power consumption, always on data processing, because analog neuromorphic core typical latency is few microseconds. So we always have real-time data processing and dramatically reduce the digital part, and we can use very tiny library or CPU core for processing this. And all of this platform, it's designed as an add-on for current design flow. So we use standard EDA tools. Now we work on top of Cadence to generate our NASP core, and we use the standard PDK from Fab. Today we cooperate with global foundries and tower semi. We use 55, 65 nanometers process. And again, what is important, the final core, final NASP core, don't consist any specific hardware requirements. So we use standard PDK, and we can tape out in any fab which is supporting this process. The 55 nanometer process is very widely acceptable and well mature. We already built first engineering chip, and now all this technology loop is silicon proven. So we just months ago finalized evaluation of first test chip, and we have full confirmation that all design flow and all simulation works correctly, and the final core work very close to initial neural net model. The business model using this platform, it's different from existing digital traditional model, and that is very important. Again, the next important thing, because what happens now in digital environment, you have a fixed processor core and billions of software variation, very flexible. You can update it. You have it's always growing. When you start build neural net, you don't know what size and structure finally you get it. The neural net, it's more like a biological, yes, it's mathematical model, but the law of growth and development is close to biological. So the final size and structure, it's not predictable. Sometimes after pruning, you may cut size of neural net for 10, 20 times. We have examples when we cut big neural net 50 times smaller from initial format with keeping the same accuracy. So it's maybe dramatical changes. And in our idea, in our business model, we generate hardware because our process is fully automated, and we generate hardware core from final neuromorphic model. So it means our core, it's always 100% fit to neural net size and structure. If it's big, we generate bigger core. If it's ultra small, we generate very tiny ultra small. So it's always optimal fit. If you use fixed neuromorphic matrix, for some application it's too big, for some application it's too small. So that is our idea. So we generate tailored product for each solution. It's application specific standard product, but that is standard product close to type of signal. I will show later how it works. Of course, it's a very important question, which everybody think that if you have a fixed hardware, how you can be flexible on the market. First, it's what market we're looking. We are not targeting for server-based application. It's not for big high-performance application. We're targeting to area where ultra low power and low latency is critical. If it's together, it's more important if you have together the same requirements. Now we identified 3 product line, which is on development in different stage. First one, NeuroSense, that is neuromorphic chip for wearables, for smartwatches and fitness tracker, which process 4 signal, PPG sensor and 3-axis AMU. So we have 4 input channels in our neuromorphic core, and output is heart rate, human activity recognitions, and few other service signal, which dramatically reduce power from digital part. So we did all this signal processing with less than 100 microwatt power consumption. So it dramatically drop power for the rest digital part. Now we have few core customers, and we expect first chip available in beginning of next year. The digital prototype is already working, accessible, so we are doing the proof of concept test with our partners. What is important? Because we use neural net for signal processing. That model is universal for any type of PPG sensor. So we use few different PPG sensor for training, and now it's agnostic to what type of PPG sensor you use or what type of IMU sensor you use. If you have PPG, you can use this NeuroSense neuromorphic model. That's what I mean, application specific, that is for smartwatches, but standard product. You can plug and play using any smartwatches. The second line is a voice processing product focused for, we have few applications. I also show the details, voice activation device, voice extraction product, keyword recognitions, all that kind of application. Here, again, it's a standard product. If you have a voice activation solution, it works in any languages, any voices. And third line, that is specific for industry IoT market, to solve problem for wireless vibration sensors for predictive maintenance market. Now the industry look for wide adoption of wireless sensor, but the problem is how to reduce data transfer, because vibration, it's a generated huge volume of data. So we offer to shift pre-processing close to the sensor. So we use our neuromorphic opportunity with ultra low power, doing pre-processing of data on top of vibration sensor. Now I am explaining a little more in details about this application. So that is how work the first NeuroSense model in typical smartwatch architecture. So we replace digital sensor MCU completely, drop power consumption for data processing, plus we can reduce sampling rate. So totally it's approximately 40% of whole system power savings. And that is in always on mode. So that numbers shows in every seconds detection of heart rate and human activity recognition. Human activity recognition, it's unique feature for our neuromorphic chip. Now it's available only in cloud connecting mode. And it's a very good example how efficiency of analog neuromorphic pre-processing and digital classification. The analog neuromorphic core have an input accelerometer signal, and output, it's a unique digital code. It's like a digital fingerprint of your personal physical activity, which is stable compared with what you're doing. So if you do cycling, every time when you personally, a client doing cycling, we generate the same digital fingerprint. It's like a digital pattern of your movements. And then on application level, in digital part, you can classify this code, you can memorize it, you can name it, group, regroup, and very flexible work with that. So the neuro core generate stable digital pattern and classification and decision in digital layer, but the data flow is dramatically lower. We have 3-axis accelerometer, and output is only 16 bytes of code every second. So it's ultra low data transfer. Of course, it's reduced power from digital side too. So that is how works combination, how works our hybrid solution. And we can use this in many other applications. Neuro voice, that is very interesting and we think unique feature for voice extraction concept. Our brain can detect human voice and extract from any other ambient noise. We can discuss with our counterparty in very, very noisy place and we can understand. Of course, if we have a good hearing level. And I think everybody knows the problem, how difficult speak was from a noisy airport or noisy street. And that what we try to solve. We already have the digital prototype of neural net, which can extract human voice with any other sounds. Please listen, that is the first example of sounds, standard problem. You talk and your cat going around you.
Yet the physiognomy of the people, when more closely examined, was far from exhibiting the indifference of stupidity. Their features were rough.
Not comfort if you talk by phone. This here you can listen the same signal, that is exactly the same signal passing through NASP neural net.
Yet the physiognomy of the people, when more closely examined, was far from exhibiting the indifference of stupidity. Their features were rough, but remarkably intelligent.
It's magic. Cut is completely noise. It's completely cutted, and that happens in any type of noise, including industrial, highway, all type of noise. And the benefits of that solution: so we have a analog interface, so we can take signal from any type of microphone, digital, analog, it doesn't matter, and clean human voice from any noises. So that solution, it's revolutionary for, especially for hearing aid systems, for two-way radios, and then of course in the future we're looking for earbuds and all these things where you use for communication. And that is in ultra low power, no any resource from CPU, so you don't need the digital resources for that. We just clean it signal itself. The next application, VibraSense. More details about this. We use the same idea as before. I'm explaining about human activity recognition, where we generate pattern of human movements. The same type of pre-processing we can did for vibration signal. Now for 20 kilohertz noise signal, vibration, it's a noise signal, and it's not compressible signal. You need approximately 1 megabit per second data transfer to have full bandwidth signal. Industry use a lot of tricks to reduce the data, to cut the bandwidth, to transfer limited volume of the data, and many other things. But what we can offer, if we shift pre-processing on top of vibration signal, we can transfer only pattern of vibration. And for PDM system, where you did detection of your abnormality, you don't need analyze the full data. You can only analyze this pattern and build your own database of this pattern, which is unique for your devices. And finally, very efficiently detect any type of abnormalities using only just 100 to 200 bytes per second data transfer required for this. So it's open opportunity for using narrowband wireless system like LoRa and others to online monitoring very wide area of applications, many devices. And that product now on the process. We expect the digital prototype will be ready in next 4 or 5 months. And next year, we think to launch this product available in silicon. Again, I just pay attention that it's application specific for vibration, but standard product. So we can generate pattern from any type of vibration in 20 kilohertz range. So it's a standard product, which can be applicable for any market. Classification, it's still in digital. I use the same PDM system as today. So that is three current product line where we focused. But we think the platform, the NASP platform, and the concept may be very widely adopted for many other applications. So, and we are, of course, open for cooperation with partners. And that is our business model in all three directions. We have a partnership with industry players, and the all products created with partnership with different vendors. We think that application may be very applicable for other healthcare monitoring application. We have a few partnership about potential glucose monitoring, blood pressure monitoring devices, not in level of medical device, but for healthcare monitoring. Also, it may be very interesting for brushless motor controllers for automotive industry, because the power is not a problem, but latency for that type of controllers, it's a issue, and we can solve this problem with latency for that type of controllers. 3D mapping, our next generation of product will be also available in image processing. It requires more complicated technology, and now we are shift image processing to second version of our platform, but technically it's possible. And few application like indoor navigation, 3D mapping also may be interesting to realize in NASP platform. So that is overview, and maybe I see it's a few questions. Maybe it's better if we jump to Q&A and I'm answer for questions. So may I start?
Thank you so much, Alexander, for this great talk and presentation. Very interesting. Yes, we have actually received several questions. We can start with the first question. So the first question is for Mark Alia. And his question is, can you kindly elaborate further on how the trained neural network is converted to an NASP?
Yeah, I see the questions. So we have a special software compiler, and when a neural net is trained, and we can take in few representation in Keras TensorFlow format or PyTorch format, then we put this to our compiler. Of course, for verification, we need some test vector, so we need test database, and several steps of conversion. We always control, we call this quantization error, because when you shift from ideal model to physical model, of course, you lose some accuracy, but typically it's very, very small and not critical. But we have a few steps of that control. And finally, we generate netlist for cadence. The final result, it's a netlist which consists neurons, connection, and weights. And we, again, the part of our compiler, it's a final netlist quality level check, and we can see what is the difference between initial ideal mathematical model and final physical model.
Thank you. The other question is, can resistors representing weights be reprogrammed, or their values are specified in early stages when designing and producing the chip?
Yeah, that is, it's a two-part of this questions. First of all, as I mentioned, we use hybrid solution where we split neural net to fixed part and flexible part. So in fixed part, you don't need to reprogram it your resistors, because all training is done before in digital model. But because our resistors, it's a separate layer, for next generation, for example, now we introduce NeuroSense 1.0 version. A few years later, maybe we will adapt and train better the model. For new version, we will change only one mask layer. So it's a mask programmable layer of new resistors. So we don't need to redesign new chip. So all our resistor generation is just one layer in mask. But yes, it will be physically new chip. And that's why we call this application specific product. So the neural core generated, for example, for PPG sensor processing, that chip can't be used for voice processing, for example. It's two different chips.
Thank you. The other question is, what does that mean? We need a new chip for every fine-tuned model. I think you've already addressed some of that.
Yeah, I'm able to answer for this. It's the same questions.
And the next one is, the technology seems similar to FPGA versus FPGAs, analog arrays versus gate arrays. For analog arrays, switch capacitors are used to build programmable analog circuits.
It's another technical way to realize this concept. Yes, you are generally looks the same direction, but again, because we generate final core from fully optimized model, our final core is optimal size. And yes, it's for example, AI Storm use switched capacitors for weights representation. That is now another way to build this analog core. It's possible. Our opinion that it's slightly too difficult, and our way it's more economically viable. So that's a question about volume and final economic model. But yes, it's very close. It's a different hardware realization of that idea.
Mm-hmm. And the next question is, this is a general question. So I'm currently working as an embedded firmware engineer with more than 2 years experience in gaining knowledge on ML and AI through online masters, basics of tinyML. Can you say something about the job?
Yes, we have Polyn.ai. You can contact with us through our website, and welcome. We are ready to discuss about, and that is my general welcome for any opportunity of cooperation. We are open not only about job opportunity, but maybe some product development opportunity. Please visit our Polyn.ai website and contact section. Of course, you can contact with us directly.
Okay, thank you. Next question is, what is a typical number of neural network parameters size per chip?
Again, so because we are flexible, so we can generate any size. For example, now we have from 10,000 neurons to few 100,000 of neurons product size, but generally is no limit. Again, from economical reason, we think our technology will work well up to 1 million of physical neurons. But again, the physical neurons, it's not equal to mathematical neurons. For example, using our mathematical conversion process, we can take more than 10 millions neurons, and that is 100 millions of parameters neural net. And then finally, we will have less 1 million physical neurons in our chip. So it's very complicated mathematical process and no direct answer for this. But today, for one-dimensional signal, like voice, vibration, PPG, IMU, and that kind of signal, the neural net core, it's more than enough. The size, it's more than enough.
Thank you. And the next question is, how is neural sense better than the noise canceling mechanism done on headsets available in the markets today?
It's a very simple answer. The noise cancelling, it's a stupid mechanism. They don't understand where is human voice, where is another sound. And if you have two sound signal coming to your microphone, the noise cancellation can't recognize what is a useful signal, what is a bad signal. Noise cancellation perfectly work for a noise which generated in connection line. That is perfectly. But noise cancellation doesn't work when you need to separate two signals coming to your microphone. Not to your hair. It's not noise cancellation for you surrounding you. That is noise cancellation, which is in incoming signal. If your counterparty speaking, for example, in noisy place. That is fundamental differences of voice extraction and noise cancellation. But disadvantage, yes, we have a big disadvantage. That mechanism don't work with music, for example, because neural net recognize only human voice, and music, it's a noise for neural net. So neural net will cut any music, everything. So you listen only speaking. That is trade-off. That is why we think finally you need both noise cancellation for reduce noise in connecting line and for music, for example, and voice extraction when you start speaking. But again, our chip recognize when you start speaking and automatically switch on off the system. So it means that if you silent, the voice extraction off, so you have a full channel open. So that is the differences between noise cancellation, which is old style, and AI-driven voice extraction.
So Alexander, in terms of being able to recognize music, I think it would be able to train a new model on your neural model.
I think it's fundamentally difficult because human voice have a very specific pattern which you can recognize. Music, it's so wide, so it's from jazz to classical music. I think it's close to impossible to train neural net detect music. Maybe many years later.
Maybe you narrow it to one type of music, maybe classical or something.
maybe, but we don't see demand for this. We don't, because for music, noise cancellation work perfectly. That the noise cancellation system work very good for music, because music, again, when you listen music, your source of signal, it's clean, because music, it's some professional data. So, and the music itself, they don't consist noise. The noise, it's through your system, maybe it's around you, but music, it's clear signal. Mm-hmm. But what happened if, for example, you listen translation of music and somebody cry in that area? No, any noise cancellation system helps you.
That's true. Yeah. Thank you. And another question is, for VibroSense, is the digital imprint application agnostic? Does the output from NASP preserve key characteristics of vibration signal?
Yes. Again, we detect pattern, so we are not take classification to NASP core. So we give you pattern. For example, you have bearings. You put vibration signal, and this is new, well-working bearings. You put sensor with NASP core and generate some 200 bytes. So it's not 200. The pattern for vibration signal is approximately 700 bits per one frame. So you have these 700 bits, and that is a pattern for good condition. Then few times later, you have some abnormality. That pattern will be changing. You have the same 700 bits, but the geometry of this multidimensional pattern is changing. So, and you are, as the owner of your device, recognize this new pattern, memorize, and next time you know that after few, I don't know, months of works, your bearings generate that type of patterns. What is important? That pattern is stable. It means that if you use the next bearings and you receive the same pattern, you can understand what happens. So classification of the pattern, that is on application level. We have few partners who work in PDM service segment. So they did classification. That is not our side. We guarantee that you will have a stable and repetitive pattern from the same type of equipment. But from another type of equipment, you will have another pattern. So that is like a fingerprint for your identity. The fingerprint looks the same, but it's unique for different people.
Thank you. Next question is there any correlation to the neuromorphic processors available? Is the memory weight set on resistors component, or is there any processing that takes place alongside the memory?
But our resistors array, it's a memory. So that is, it's like the kind of memory. So we don't have a separate memory. I'm not fully understand the question, but we don't have any digital memory. We don't have any data transfer. Resistors array, is it some, that is the memory for our neural net.
Yes, it's a resistive memory, right?
Yeah, it's resistive memory.
Okay, and next question is, how can we use these models like VibroSense also, or what kind of hardware do your system support? Is there any guide of getting started?
I'm just answering for this. We agnostic to type of hardware. So the VibroSense can be applicable for any rotating part where you have vibration with no limitation. And again, if you want, you can contact with us by our website and we're ready to discuss, but it's agnostic to type of equipment because again, we generate digital fingerprint of your vibration. And definition of this, that is another question, how to define this.
Thank you. And the other question is, how can we use these models? Like, I think you've already...
No, we already answered for this question. Next thing.
Next one is, what kind of tools can we use in simulation of data while designing a device which is working on the neuromorphic principles, and how neuromorphic computing can be helpful in image processing?
I'm not sure that it's the right question for me, because we use the existing environment. So we work in TensorFlow, and we use the standard tools for digital model simulation. So and that is, we take the industry standard. So we don't develop that part. So that is. And the image processing, again, it's a lot of application about image processing. We are not today focused for that product, so we don't have our own product in that area. But what I know, it's a lot of application where the neuromorphic model is very helpful for image processing. But again, I think it's not directly for me that question. We use a standard industry available tool. We don't generate nothing specific for us.
I think maybe the question is that, is there a tool that simulates how you would, maybe the accuracy or the energy savings that you...
Yes, of course, we use for accuracy, we compare how work ideal initial digital model of neural net and how work after conversion. So we just use a test data set and we pass through initial ideal model and the final model, and we see what is the output differences. And the final simulation is made in Cadence Virtuoso to simulate the future power consumption and latency. And our test chip, which is now in silicon, confirms that cadence simulated very close to real results. So it's the cadence virtuosa, it's simulated neural net core.
Okay, great, thank you. Next question, are you using direct sensor to spike converters to generate spikes similar to DVS event cameras?
No, we don't use spike. Our core work with levels, so we are not work like a spiking neural net. Our internal data representation, it's just voltage, so it's not spike, it's not impulse. So we don't work with event, so we don't need special event sensors. We work with standard analog signal, like a microphone signal, so it's standard analog input. The same for PPG signal, so we don't need spike.
Mm-hmm. Thank you. And could you provide publications on this technology? That's the next question.
We have a white paper available in our website. That is the most detailed publication. The few articles now publishing, but the best details you can find in our website in white paper section.
Thank you. Next, how do you overcome mismatch on the analog neurons, or is the precision enough for low power sensory processing?
It's a very important question, and that I'm surprised that it's so not in the first line. And that is unique property of analog neuromorphic structure, because if you use old style analog computer and connect your analog calculation blocks to a line, your error is multiples. The first line might multiple to second line, and finally you have a very, very big error.
Yeah.
And you need a very stable temperature and voltage environment to keep your computing chain in some rational accuracy. But it's a few very unique properties when you connect analog elements as network. Train it neural net, they have self-compensating error mechanism inside the neural net. That is the first. So the error, it's not multiple from layer to layer. It's less than linear growth of error level. And second, what is our own proprietary technology? Because we know the technology mismatch, so we use well-known technology, and we know statistic of the semiconductor process. We implement this mismatch in the part of our conversion process. So when we do conversion of mathematical conversion of initial ideal neural net, we did uptrain of neural net using this mismatch flow. So that is the curve of mismatch, and that is additional compensation. That is two mechanisms. The first is self-compensation for training neural net, and second, we did additional compensation when we make conversion. Finally, the stability of analog neuromorphic, again, it's not old style analog computing model, and that is very important. It's analog neuromorphic core. It's very stable like a digital system. We have a very extremely high robustness and no any noise and PVT factor influence for output result. That is very, very important property, which open opportunity for that. So otherwise, of course, if you have 100,000 of operational amplifier, and it's not possible to build super low DC offset for all these 100,000. You have a few microvolts in output, and then multiple one to each other, and finally you have a total mess. But answer, no, that not happens.
Yeah, thank you. Olga, just checking on the time. Can we, do we have time maybe for more questions? A few more questions?
Yeah, just I can, for recurring neural network, it's no problem. Yes, we did this. It's simple answer, yes. For image signal, yes, noise and image can be separated, but again, we shift this for next generation, not now. Neuro drive, unfortunately, it's too long to explain. That is a solution for fast controllers for brushless motor. That the tinyML, so we are not used directly tinyML because we are not digital, but the initially of the concept of tinyML was based in our research, but today not. I can't answer about resistive memory. It's too many technical details. We think about resistive RAM. Theoretically, it's possible. Theoretically, it's possible. Not, of course, we are not open our source code in GitHub because that is our own proprietary neural net. Yes, it's possible to overcome sensor drift. That is perfectly what neural net can do. We have precision from 8 to 9 bits. That is output precision. Today, it's more than enough. All application where we work, 8-9 bit precision, it's okay. Theoretically, it's possible up to 12, but it requires more complicated schematic, and we don't see reason for this.
And in terms of the precision, are you planning to go lower, like, for example, 4 bits or?
It's not necessary because the standard mechanism generates 8-9 bit precision. We don't have benefits if we go lower. So we need additional solution to go higher. And that is question. But that is not digital system. So where you have the direct link between precision and complexity. And in analog, it's not that. So.
Okay, great. Thank you so much for addressing almost pretty much all the questions. And thank you so much for your great talk and presentation, very inspiring.
Thank you. And again, welcome to our website. And we are happy to discuss and keep in contact.
Thank you. And again, I would like to thank our strategic partners for their commitment, and also special thanks to the executive strategic partners, ARM.ai, for working on the latest in AI trends, technologies, and best practices from ARM. Edge Impulse, the leading development platform for Edge ML. Qualcomm, AI research, advancing AI research to make efficient AI ubiquitous. Sentient, making edge AI a reality. And also very special thanks to our Platinum strategic partners, DeepLight for fastest video analytics solutions on ARM CPUs, Klika Tech, global IoT solutions, high value and safety critical use cases with Reality AI, which delivers tinyML software that covers the full engineering lifecycle. And Renesas, which is enabling the next generation for AI-powered solutions that will revolutionize every industry sector. Sony Semiconductor Solutions Corporation. And also special thanks to our gold strategic partners, Analog Devices, where what if becomes what is. PhotoHub, making over-the-air firmware and ML models updates simple and accessible. And Latent AI, which brings efficient inference platforms. NXP, together we accelerate the breakthroughs that advance our world. And Seed Studio for deploying tinyML into the real world, plug and play ML. And SensiML for analytics toolkit suite. And ST Microelectronics providing extensive solutions to make tiny machine learning easy. Synaptics for engineering exceptional experiences, SynSense for building, sensing, and inference hardware for ultra-low power. And also a special thanks to our silver strategic partners, Ion Devices, EMSA, Greenwaves, Gravity, HOTC, Image, Mob, ITMist, Nota AI, OctoML, Prophecy, Kixo, Rixan, SAP, Silicon Labs, Stream Analyze, and TDK EventSense. Again, a quick reminder that our next tinyML talk will happen on Wednesday, the 29th of June. I hope you join us again for a very interesting talk. And this is just, our copyright notice. Again, I would like to thank you for being with us today. Also thank our speaker, Alexander, for a great talk and great insights. And thank you again.